The acceleration of an elevator as a function of time is shown in this top graph, and you're told that at time t equals 0, the elevator is at a vertical position of 0 with initial vertical velocity of 0. So the first thing we want to do for part A is determine the velocity of the elevator at the end of each 5-second time interval. So let's look at this first 5-second time interval from here to here. Now, whenever you have a 0 acceleration, that can mean one of two things. Either the object is not moving, or it's moving at a constant velocity. So how do you know which it is? Well, you were told for this problem that at the beginning, the elevator was not moving. So because it was not moving to begin with, that means it's still going to be not moving right here. You always look at what's happening right before the 0 acceleration period started. If it was not moving at this point, then it's not going to be moving here. If it was moving at this point, then whatever speed it had right here, it's going to have the same speed as it goes along here. So for 0 to 5 seconds, the time at the end of that 5-second time interval is going to be 0 meters per second. All right, let's look at the next 5-second time interval. From 5 to 10 seconds, we see the elevator has an acceleration of 2 meters per second squared. And whenever you have an acceleration versus time graph, it's the area under that graph that gives you the velocity. So the area of this, it's a 2 by 5 rectangle. So the area is 10, which means that from 5 seconds to 10 seconds, the elevator went up to a speed of 10 meters per second. All right, so at this point right here, at 10 seconds, the elevator is moving at a speed of 10 meters per second. Now we're back to 0 acceleration. So we said it could be one of two things, either not moving or moving at a constant velocity. You base it on what was just happening. And what was just happening was that the elevator was moving. The elevator had gradually sped up from 0 to 10 meters per second. So at this point, it's already moving at 10 meters per second. So now it's just going to stay at a constant velocity of 10 meters per second. It's not going to go back down to 0 because there would have to be a deceleration or a negative area under the graph before this came. So it's moving at a constant velocity of 10 meters per second, which means at the end of 15 seconds, it is still moving at 10 meters per second. All right, so what's happening in this last region? The area of this rectangle, it's a 2 by 5 rectangle, but it's below the axis, so it is negative 10. What that means is since the elevator was moving at 10 meters per second when it was right here, we're going to add that negative 10 onto it, which means the elevator is just slowing back down to 0. So at the end of that last time interval, we can just say that the elevator's velocity is back down to 0 meters per second. So before we do the position table, let's skip down to part C and just draw the corresponding graph of the velocity. So we know that the velocity was initially 0, and it didn't move for those first 5 seconds. So just draw a horizontal line at 0. And then we know that the velocity increased slowly up to 10 meters per second. So it's not a jump up to 10, it's just a gradual increase up to 10 meters per second. So it's going to be a straight line sloping upward. Then it stayed constant at 10 meters per second. So we're going to continue this by drawing a horizontal line from 10 to 15 seconds. And then it decelerated back down to 0. So the last part will just go back down to 0 at the 20-second mark. And then you can compare this graph to what we have for the acceleration now. Here we have 0 slope, and here we have 0 slope, which means the acceleration should be 0 and 0, since acceleration is the slope of velocity. Here we have a positive slope. This graph is positive, and here we have a negative slope, and this graph is negative. All right, let's figure out the position of the elevator. So to get position, you actually use the area under the velocity versus time graph. So let's now focus on this graph, and see what we can figure out with the area. So under this part right here, the area is 0, and the elevator was originally at a position of 0, so it's just going to stay at that position 0. It's like the elevator is just kind of sitting there on the bottom floor. So the first reading in the table is going to be 0 meters. Now let's look at this part of the graph. It forms a triangle. This is 5 by 10. So 1/2 base times height is 1/2 times 5 times 10, or 25. So the area of the triangle, I'll just write it right here, is 25 meters. So that's where it's going to be located after 10 seconds. Now let's go to the area of this next interval. This is a rectangle that measures a 5 by 10, so it's 50 meters altogether. So if I just write the 50 meters here, but be careful on this, that doesn't mean the elevator is located at 50 meters at the end of it. It's 50 meters ahead of where it was, or above where it was, and it was already at 25 meters from that part. So it's 25 meters plus an additional 50 meters, which is now going to put the elevator at 75 meters. And then the last triangle is symmetrical with this triangle, so that means this is going to be 25 meters also. But then do the same thing as before. We have to add that 25 meters on to where the elevator currently is. So 75 plus 25 puts the elevator at 100 meters. Okay, let's draw the graph of velocity versus time, or position versus time. So the elevator started at 0, and it just stayed there for the first 5 seconds. But now, instead of putting the graph directly on there, let me just draw some dots. So we know at the 10-second mark that the elevator is located at 25 meters. So I'll put a dot right around 25 meters. Then at the 15-second mark, it was located at 75 meters. So I'll put a dot around there. And then at 20 seconds, it was located at 100 meters. Now we know in this region right here, from 10 to 15 seconds, the elevator is moving at a constant velocity. And the way you depict a constant velocity on a position versus time graph is with a straight line. So we need to have a straight line connecting those 2 points. Now the other 2 parts of this graph, we have an acceleration. So right here, we have a positive acceleration in the positive direction, which the graph is going to look concave up. So if I go down to this graph, I need to draw a concave up line that kind of makes a smooth transition from one part of the graph to another. And then in this last part, now we have it's slowing down, still in the positive direction, but slowing down. So that's going to be concave down. So this last part will look like, let me redo that. Last part will look like this. So it makes kind of like this, sort of like an S shape for the position graph. But notice that the elevator never went in the downward direction. It was moving up the entire time. It was just not moving right here, then accelerating up, and then moving at a constant velocity, and then slowing down until it stopped. And for part D, suppose instead of representing the motion of an elevator, the acceleration versus time graph shown represents the motion of a ball on a track. So let's just draw a track that would generate the same type of graph. So we have 0 acceleration for the first 5 seconds. So the way to get 0 acceleration on a track is by, let's put the ball down here, and you get 0 acceleration by having a horizontal section of the track, because then it's just moving at a constant velocity along that horizontal section. So we can indicate that by drawing a horizontal line under where the ball is. Then we have a period of positive acceleration. So to get positive acceleration, speeding up, we want it to go down the track. So I can make the track dip down like this. So it's accelerating down that part for 5 seconds. Then it is back to 0 acceleration. So it's going to have to be horizontal again. Now the ball's moving much faster here because it just went downhill, so I'm going to make this part of the track longer since the ball has 5 seconds to be on that part. And then finally, we have the slowing down region. So to get that, we're just going to make the track go back upward like that. So now if you follow the motion of the ball, constant velocity, which is 0 acceleration, then increasing speed, that's the positive acceleration, constant velocity, that's the 0 acceleration, and up here is decreasing speed, so negative acceleration.